model is constructed of a wire mesh roof structure, which is supported by 4 columns made out of springs. This structure provides the ability to replicate the violent and dramatic motion in all directions that is seen in earthquakes. 2 pipes of equal size are suspended from the structure above. The hangers that are used are made of small diameter steel cables. This makes them flexible so that they cannot contribute to the bracing effect. 1 pipe is braced to demonstrate the effectiveness of tension-only cable bracing. The other pipe is left unbraced to give a sense of the effects when no bracing is provided. The braces themselves are made of the same small diameter steel cables. 4-way braces have been installed at both ends of the braced pipe to provide resistance to the earthquake loads coming from any direction horizontally, which is required by the building codes. It is clear from this configuration that none of the materials used to hang or brace the pipe offer any compression resistance to movement of the pipe, and that the pipe is free to move except for the controlling effects of the geometry of the braces acting in tension only. Since the suspended pipes are more sensitive to the horizontal forces perpendicular to the pipe, we will view the application of the earthquake forces from the end view of the pipes. As you can see, it takes relatively little horizontal movement to cause the unbraced pipe to rotate upward all the way to the point that it contacts the roof structure. Notice, however, that the braced pipe does not exhibit this upward rotational movement because of the effect of the braces. The reason that the braced pipe does not rotate upward is that the dead load of the pipe helps to counter this effect. The explanation for this is really quite simple. The horizontal force required to be applied to the unbraced pipe in order to make it rotate up to the point where the hanger is at a 45-degree angle is equal to the pipe's weight. In order to make the pipe rotate upward further, the force would have to exceed the weight of the pipe. When the pipe is braced, the braces are already installed at an angle, so a horizontal force in excess of the weight of the pipe would be required to make the pipe swing further upward. The counteracting effect of the dead load varies according to the brace angle, and if the horizontal force is sufficient to exceed this effect, compression resistance through the pipe hanger must be provided. The mathematical formula to make this determination is the horizontal force divided by the tangent of the brace angle from vertical minus the weight of the component within the zone of influence of the brace. This resistance to the upward rotational movement can be seen and felt by pushing the braced pipe in the horizontal direction. Note that the resistance is sufficient to make the roof structure move until sufficient horizontal force is applied to overcome the force of gravity. It should be noted at this point that these principles apply to both tension-only cable bracing and combination tension-compression bracing such as strut, angle iron, or pipe for the primary brace element. However, the downward vertical reaction to the horizontal load is a much different story. Strut, angle iron, and pipe-type braces must resist the horizontal earthquake forces in tension half of the time and in compression the other half of the time. When resisting the forces in compression, there will be a downward vertical reaction. In that case, the dead load of the pipe is added to the downward vertical reaction, and this resultant downward force can and does cause hanger failures. This is not an issue for cable braces because they cannot act in compression. Additionally, because strut, angle iron, and pipe-type braces must act in compression, they must be designed to resist buckling. This requires compliance with Euler's least radius of gyration formula, which limits the length of compression members. Conversely, cable bracing lengths are unlimited. Now let's see a little more violent earthquake simulation with the shake table model. The cable brace piping exhibits only a slight twitching under circumstances that no building could be expected to survive.